All right, so let us now move into part number 2. So we are going to develop the concepts we have learned so far. We're going to develop them one step further. I'm going to go back to this linear element, the two-noded one, and I'm going to discuss the concept of the shape function. So that the shape functions are pretty much the most, I would say probably, if not the most, then probably one of the most important aspects of the finite element method. And in order to understand the method, you really need to understand them. So I'm going to focus on this part within the remaining section of the lecture today. So we had this two-noded element. We had node number 1 and node number 2. And we said that we are going to represent it in a linear way. So we have this linear equation. Better. I'm going to generalize the element now. I'm going to move one step further and assume that things are more general. So we have displacement U1 and U2 at node number 1 and node number 2. And then I'm just going to assume that we don't have x equals 0 at the beginning of the element. I'm going to assume that you have the x-axis in this direction, but the node 1 is located at x1 and node number 2 is located at x2. This is the only difference now. Instead of x1, assuming that x1 is equal to 0 and x2 is equal to L, I'm just going to have a general value for x1. So I'm still representing displacements in a linear way, ax plus b. This is the line equation I'm going to use, and I'm going to represent displacement as a line. So this is the key in what I'm going to explain. See, the line, the linear, this is the key word you need to remember. I'm going to derive now the shape functions, and then I'm going to tell you how they work. So let us just do the same process we did earlier when we did the interpolation for the displacement at x equal to x1. We have u in this equation is equal to u1, and then I can substitute x with x1 plus b, and at x is equal to x2, we have u to be equal to u2, and we have a multiplied with x2 plus b. I have two equations. This is the first, and this is the second. So I'll probably just write it. I'll put it in a box. So these two equations, I need to solve them for A1, for A and B. I have two equations. I assume that I know U1 and U2. I know the X1 and X2. I need to solve them for A and B. So this is what I'm looking for. The first thing, I can just subtract both equations. So I will have this one multiplied with -1 added to the second equation. So I will have U2 minus U1 is equal to A x2 minus A x1. And then I have minus B plus B is going to be a 0 there. So the 0, I don't need to write it down. I only have A, and A will be, in this case, U2 minus U1 divided by x2 minus x1. So this is the value of A. I can use either one of these equations and find the value of B. I just place it back into the first equation, or probably the second. It really doesn't matter. I would use the second equation. U2 is equal to A multiplied with x2. So I'm just going to write down the whole thing. U2 minus U1 divided by x2 minus x1, and multiplied with x2, and then plus B. In order to find the value of B, I will just move the whole thing to the left-hand side. So this B is going to be U2 minus U1 divided by x2 minus x1. And in order to be able to add the U2 to these guys over there, I need to multiply it with x2 minus x1. So in this case, I would have B is equal to U2 multiplied with x2 minus U2 multiplied with x1. And then I can subtract these ones in here. I need to, so the x2 also is part of it. So it is minus u2 multiplied with x2 and plus u1 multiplied with x2. And then I will have the whole thing divided by x2 minus x1. u2 x2 and u2 x2 will cancel together. I'll be left with minus u2 x1 and then plus u1 x2 and divide the whole thing by x2 minus x1. And this is the value of b. Now, if I put a and b back into this equation there, this equation here, oops. So I insert b here and a here, I will have this expression. I will have this expression there. And then if you want, you can write it in this form. It is n1 u1 plus n2 u2 with the 2. See, I'm going just to insert a and b into this equation. So I have u. I'll probably just move them down, slightly be neater this way. Yeah, clean this whole board. So this is A, and this is B. And the equation I want to insert everything in is this one. Oops. So U is equal to A. This is U2 minus U1 divided by X2 minus X1 multiplied with X added to minus U2 X1 plus U1 X2 divided by X2 minus X1. I'll just multiply X with these and add them together. So U is going to be U2 X minus U1 X minus U2 X1 plus U1 X2. And the whole thing is divided by X2 minus X1. I'm going to take everything to do with U1 first and everything to do with U2 second. So this term would include U1. This term would include U1. I'm just going to move them to one end. So I have U1 X2. This is the positive term. 9 minus U1 X divided by X2 minus X1. And then I have U2 X minus U2 X1. So I'm just going to write it here. U2 X minus U2 X1 divided by X2 minus X1. Now you take U1 and U2 as a common factor. So you have X2 minus X divided by X2 minus X1 multiplied with U1 added to U2 minus, added to X minus X1 divided by X2 minus X1 multiplied with U2. So you have U1 and U2. So this is the nodal values for the displacement. So this is the displacement at this node and at this node. So you have the nodal values for the displacement. You can find the displacement across the entire length as long as you know the coordinates for the U1 and U2 and you know the value of X. So I'm going to call these guys here, this one. And this one, I'm going to call them, I'll just write it in red because this is important. I'm going to call them N1 and N2. And this is the shape function. So this is the first time I'm going to This is the first time I'm talking about the shape functions in this class, but this is, as I said, one of the most important concepts in the finite element method. So U can be written just like N1, U1 added to N2, U2, or it's going to be N1, N2 in matrix form multiplied by U1 and U2. Now this equation here is universally correct. This is correct for any number of nodes if we're talking about one-dimensional problem, and it's correct in any number of dimensions. It's correct for 2 dimensions, 3 dimensions, 4 dimensions. It's always going to be the displacement within your element will be depending on the displacement at the nodes multiplied with the shape functions. This is, as I said, universally correct. Now I'm going to talk a little bit about the significance of the shape functions. If you want to draw these shape functions, probably this is meant to be x1, and this is meant to be x2. I'm just going to copy over the expression for the shape functions. x2 minus x divided by x2 minus x1. This is n1 and x minus x. I'll just write them down in here. n1 is x2 minus x divided by x2 minus x1. And n2 is going to be x minus x1 divided by x2 minus x1. Now you have a coordinate system. You have the x-axis. Sorry, this is meant to be the x-axis. And this is x1, and this is x2, and this is the value of the shape function. So if you draw these shape functions for any x1 and x2, you will see that at x1, n1 will be equal to 1. The amplitude of n1 is going to be 1, and it's going to be 0 at x2. The same is correct for n2 is equal to 1 and is 0 at x1. I mean, try to draw them yourself. You'll see that this is going to be the case. This is how the shape functions would look like. And now the power of this shape function, the power of writing them in this form, is the fact that no matter what displacement field you have, you can recover this using these shape functions. So for example, let us assume that this is your element. This is node at x1, this is the second node at x2, and the displacement within this element, let us say this is displacement and this is x, at x1 and x2, you have this pattern of displacement. So the displacement here is 5 and here is 10, just for the sake of argument. Now these shape functions can recover the equation of this line by just multiplying this node with 10 and this node with 5. So you know the value of the displacement at x2, this is 10, and the value of the displacement at x1, this is 5. You multiply this node with 10 and this node with 5. You add up the two lines. They are going to recover exactly this line in there. If instead of this one, you are going to look into another one. For example, this is the value of the displacement at this node is 4, and at this node is minus 8, for example. You multiply n2 with minus 8 and n1 with 4, and you are going to recover exactly this line by adding these two equations, these two lines. Now they can recover, basically these two shape functions, they can recover any pattern of displacement that is happening between node number 1 and node number 2. Any pattern of this displacement can be recovered as long as the pattern of displacement is going to be a line. And this is the strength of the shape functions. So they can basically reconstruct the entire displacement within your element just using the value of the displacement at the nodes. All right, I'm repeating this because I think this is pretty much the focal point of this lecture today. Now, I'm going to ask you a question. What about if the displacement within this element would look like this? I mean, it's possible. It's possible. Displacement can't look like anything. They result from stresses, and the stresses would result from forces, and force can be applied in any way. So you don't control the forces that are applied on your structure. So they can result, the forces, they can result into any pattern of displacement. So how about displacement looking like this? Would you still be able to reconstruct anything with these shape functions? Do you think the shape functions would be useful in this case? And if they are not useful, then how to solve this sort of problem? Exactly. I think I made the same point. So instead of trying to recover the whole thing using one line, because I mean, the best definite element method with one linear element can do is to take the displacement at this point and take the displacement at this point and interpolate everything as a line in between. So this would miss the displacement quite significantly. But instead of doing that, if you, instead of using just one element, use multiple elements, like I suggested, look at the peaks. So you have one node here, and then in between the nodes, you interpolate using lines. So this is 1, this is 2, and this is 3. So this line is recovering the polynomial here, is recovering the polynomial with a much better approximation compared to the original approximation. So these elements, they still can be very efficient for recovering complex patterns of displacement, but you really need to be careful on how you create your mesh. Now, if you don't know anything, if you really want to apply brutal force to solve the problem and solve any problem, then you can divide it into many small elements. And any shape, really any shape, can be divided into a summation of lines, a combination of lines. And think about any curve you want. And when you divide it into enough number of lines, then these lines can really represent this complex shape. It doesn't really make any big difference from the computer point of view. This is just a simple thing to do. Now, this principle of brutal force can recover any complex displacement pattern. Obviously, it can do that, but it is only your force that is available to solve the problem. So if you have a strong computer, you probably can do this brutal force. If you don't have a very strong computer, probably need to be more clever. And there'll be always problems where you need to be clever to solve. You cannot use just brutal force to solve them, because there will be always problems that will exceed your force. So you need to be careful and you need to be thinking on how to solve the problem. You probably the example probably helped you to understand the shape function in a slightly better way. All right, so we have a problem. We have a cantilever. The cantilever is fixed at this end, and there will be 100 Newton applied at the free end. The length of the cantilever is 4 meters. The cross section is 0.1. The elasticity modulus is 200,000 Newton over square millimeters. Now, we can solve this problem using one element. One element is enough to solve this problem. Oops. So you have one element to do the whole domain. You have the EA over L is the material properties. You can just write the stiffness matrix for this element. You substitute the boundary conditions. U1 is 0 and P2 is 100. You solve this problem, and this is very easy to solve if you do the reduced system. So you remove the row and the column associated with the 0, and you have U2 multiplied with EA over L is equal to 100, or 100, or U2 is equal to 100L divided by EA. So this is the value of U2. If you calculate the numerical value of U2, this is going to be 2 to the power 2 multiplied by 10 to the power minus 5. You substitute the first equation and you get the reaction. This is 100. This is easy to solve. I'm not going to solve it. It's just easy to solve. So I'm going now to use the shape functions. We are interested in finding the displacement at 1 meter from the support. So this is roughly here, and 2 meters from the support. This is pretty much the mid length, and 3.5 meters from the support. This is around here. So if you want to put it in terms of coordinates, you can assume that X is starting here, and this is X equal to 0. X here is equal to 1. X here is equal to 2. X here is equal to 3.5, and obviously at the end, X is equal to 4. So you are interested in finding the displacement exactly at X1, X2, and X3.5. This is what you want to do. And in order to do this, you need to use the shape functions. I'm just going to do it in a minute. So you have the displacement u2. u2 is equal to 2, 10 minus 5 millimeters, right? This is the value we have for the displacement. It's 2, 10 to the power minus 5 millimeters. We're going to use the shape functions. The shape functions, we have them written in here. N1 is equal to x2 minus x2 over x1. N2 is x minus x1, x2 over x. So I'm just going to use these numbers. Let us look into this element here. This is the element. x1 at node number 1 is equal to 0. x2 at the end of the length is equal to 4. So the shape function would look like this. N1 is x2 minus x divided by x2 minus x1. This is equal to 4. This is equal to 0. This is equal to 4. I'm just going to write it as 4 minus x divided by 4. If you look into N2, the expression for the N2 is x minus x1 divided by x2 minus x1. And again, this is equal to 0. This is equal to 0. This is equal to 4. So I'm just going to write it down as x divided by 4. All right, so this is N1 and this is N2. The expression for the displacement in terms of N1 and N2 is here. Probably here, yeah, it is here. So this is the expression I have for the displacement in terms of N1 and N2. So U is equal to N1, N2 multiplied by U1 and U2. Now the value of U1 is equal to 0 and the value of U2 is 2, 10 minus 5 millimeters. So I'm just going to use the shape functions over there. So U is equal to 4 minus x divided by 4. And then I have x over 4 multiplied by 0 and 2, 10 to the power minus 5. And the displacement anywhere inside the domain is going to be u equal to 0 multiplied with 4 minus x divided by 4 is going to be 0. I'll be only left with this one multiplied with this one. So I have x over 4 multiplied by 2, 10 to the power minus 5. And then I can cancel this with this. It will leave me with x over 2 multiplied by 10 to the power minus 5. And this will give me the displacement anywhere inside the element, inside my elements. I'm interested in finding the displacement. I'm interested in finding the displacement at x equal to 1, at x equal to 2, and at x equal to 3.5. So at x equal to 1, just move this to the top. At x equal to 1, we have half multiplied with 10 minus 5, or you just write it, sorry, this is u, or you just write it 0.5, 10 to the power minus 5, or you just write it 5, 10 to the power minus 4. I really don't care how you write it. It's completely up to you. At x equal to 2, you have u to be 2 divided by 2 multiplied with 10 to the power minus 5, or this is 1, 10 to the power minus 5. And at x equal to 3.5, you have u to be 3.5 divided by 2, 10 to the power minus 5. 3.5 divided by 2, this is going to be 1.75, 10 to the power minus 5. And these are all in millimeters. So do you have any questions? All right, I've got one question, and this was the question I'm going to ask you. Actually, I've made a mistake in these calculations. Now, the mistake still resulted into a correct solution. So if you look into the unit for the displacement I have in there, this is in millimeters. if you look into the length I inserted in these shape functions, 4, 4, and 3.5, and 2, and 1, so this is all inserted in meters. Now, my answer is still correct. Do you know why is that? Shape functions are unitless, they are ratios. So they cancel, the unit will cancel, and you don't have any unit for the shape function. So the remaining unit is going to be the unit of the displacement you insert in there. And think about it, if you have the shape functions with a unit, then you have the shape function to be a unit of meter and multiplied by the displacement, in this case, going to be in millimeters. So the resulting displacement is going to be meters times millimeters, which is not a unit for displacement. This is a unit of area. Now, usually unit for area, you have it in square millimeters or square meters. I have solved one example. I want you to solve one example yourself. This is the example for you to solve. I mean, first of all, I want you to solve this problem to identify the displacement at the nodes. So solve the problem just like the standard problem we have been solving. This is 2 elements. You need to work on that. And then I want you to find the displacement at 1 meter from the support, 1.5 meter from the support, and 3.5 meters from the support. So the stiffness matrix for the first element, I've written that for you here. The stiffness matrix for the second element, I've written that for you here. Just do the assembly into the big system, where you have zeros. And then solve the big system. Get me the value of U1 and U2 and U3. And then I want you to find the displacement at these locations. Okay? It's going to take you some thinking. I really want you to think. So solve the problem and then think about the displacement, how to identify them. I'm going to come back to that in 5 minutes. So just take 5 minutes, try to solve this, and then we can discuss it further. Okay, I'm also going to show you the displacement. So the solution for this problem is, so these are the values for the displacement, 7, 10 to the power minus 6 millimeters at the second node, and 1.1, 10 to the power minus 5 at the third node. So this is the solution. So to solve this problem, we can use 2 elements. So this is element number 1, and this is element number 2. I'm just drawing the nodes not quite on top of each other, but you know that they are actually should be on top of each other. Taking them from here, 7 and 11. So it is U1 is equal to 0, U2 is 7, 10 minus 5, and U3 is 11, 10 minus 5. I'm just using 11, not 1.1. So it should be 10 to the power minus 6 here. So just to make it 10 to the power minus 6. We have 7. Oops. We have 7, 10 to the power minus 6. And 1.1, 10 to the power minus 5, or 11, 10 to the power minus 6. So I've just wrote it as 11, 10 to the power minus 6, just to have these numbers here consistently in there. Now, I'm going to use the shape functions. Okay, Mohammed also have the answers. I'm just going to write the shape functions expression. N1 is x2 minus x divided by x2 minus x1. N2 is x minus x1 divided by x2 minus x1. Now, we are starting, I mean, for the first cross section, this is 1 meter from the support. 1 meter from the support is happening within the first element. So this is the first element. So in order to be able to find the expression for the displacement, I need to look inside the first element. All right. So in this case, x2 and x1 will belong to the first element. So the first element, we have x1 to be 0 and x2 to be 2. So I'm going to replace these numbers in there. So I'm just writing down here for the first element. We have N1 to be x2 is 2 minus x divided by x2 is 2 minus x1 is 0. So it is going to be divided by 2. And n2 is going to be x minus 0. x1 is 0. And x2 minus x1 is 2. And then I have the displacement to be, in this case, refusing to move down. So I have u to be equal to n1, n2 multiplied by the displacements I have in there. So this is displacement at the first node. Displacement at this node is u1, and this node is u2. So I have 0 and 7, 10 to the power minus 6, obviously millimeters, 0, 7, 10 minus 6 millimeters. And then I have the expression for n1. This is this one, and n2 is x2 over L. So it's x over L. 0 multiplied with n1 is going to be 0. And then I have 7, 10 to the power minus 6 multiplied with n2. And the displacement is x over 2 multiplied by 7, 10 to the power minus 6. Now, I'm interested in finding the displacements at x equal to 1. So this will be half times 7 minus 6. So this is going to be 3.5, 10 to the power minus 6 millimeters. Okay, Greta also has the answers. If you look into the second cross-section we are interested in is 1.5 from the support. So 1.5 is still within the first element, is happening here. So this is within the first element. So I need to use the shape functions of the first element, and u is equal to x over 2, 7, 10 to the power minus 6. So it is 1.5 divided by 2 times 7 times 10 to the power minus 6. And this is basically, 5.25. What is the answer for that? It's 525, 10 to the power minus 6. If you multiply them, again, in millimeters. If you come to the last cross-section, the last cross-section is 3.5 and is happening really here. So it is happening within the second element. So I need to write down the shape functions for the second element. And the second element, we have x1 at this node is equal to 2. X2 at this node is equal to 4, all right? See, the coordinate here is 2, and here is 4. So x2 is equal, x1 for the second element is 2, and x2 for the second element is equal to 4. I need to substitute these numbers in there. I'm just repeating the same thing. Just remove these ones here. Oops. No, come on. Okay, so x2 is now, I'm getting it from here. So n1 is 4 minus x divided by x2 minus x1. It is 4 minus 2. And n2 is x minus x1, which is 2, divided by 4 minus 2. And then I have n1 to be x minus, sorry, it's 4 minus x. 4 minus x divided by 2. And n2 is x minus 2 divided by 2. Again, I'm just going to write an expression for the displacement within the second element. So the displacement is n1, n2 multiplied by u1 and u2. u1 in the second element is the displacement at this node. This node is u2 on the global system. And then the displacement at this node, which is the second local element, as a second local node, is equal to the global displacement at u3. So I have 7 10 to the power minus 6, 11 10 to the power minus 6 to be replacing U1 and U2. So it's 7 10 to the power minus 6 and 11 10 to the power minus 6. And N1 is x minus 4. Just put it in here. So it is 4 minus x divided by 2 and x minus 2 divided by 2. And then you have u, an expression for u, 4 minus x divided by 2 multiplied by 7 10 to the power minus 6 plus x minus 2 divided by 2 multiplied by 11 10 to the power minus 6. Now at x equal to 3.5, you will have u to be 4 minus 3.5 divided by 2, 7, 10 to the power minus 6, added to 3.5 minus 2 divided by 2, 10 or 11 first, 10 to the power minus 6. This is 0.5 divided by 2, it is 0.4 or 0.25, sorry. 0.5 divided by 2 is 0.25 times 7 times 10 to the minus 6. And 3.5 minus 2, this is 1.5 divided by 2, this is 0.75 times 11, 10 to the power minus 6. If you calculate them, 0.25 times, I probably need to use a calculator, is probably 0.120, sorry, this is 1.25. I think so. Is it not? Sorry, 1.75.
1.75.
Yeah. And then here we have, I think, 8.25, 10 to the power minus 6. I hope I've not made any mistakes. I think this is correct. And then you will be adding these numbers together. That is 1 is 10, 10 to the power minus 6, or is just 1, 10 to the power minus 5 millimeters.